Okay, thanks a lot to the organizers for the opportunity to both speak here and be a part of this wonderful program. It's been really fun. I've been here the whole 3 weeks and I've really enjoyed it. So thank you for all the interactions. Okay, so I'm going to tell you about this paper, 2407, this reference here with Yiming Chen and Haifeng Tang. Yiming is a postdoc at Stanford, where I was up until 3 weeks ago, and Haifeng is a graduate student. And the reason I circled his name was most of the calculations in this paper were actually done by him. But this paper uses heavily results that we wrote in a previous paper from last year, and that was with Dan Enicheku, who's a student at Stanford, and Chitrang Murdia, who's here in the audience. He's a postdoc at UPenn. So the name giant graviton goes back to some computations in ADS space, and it was first coined in a paper by McGreevy, Susskind, and Tumbas, I believe, and Rob Myers has done work on it, and many other people. And recently, people have started discussing what is the so-called giant graviton expansion of certain quantities in the dual gauge theories. And this is work that has been done by these authors, Murthy, Imamura, Ji-Hun Lee, Gyoto Kim, and many others. So in the process of explaining this giant graviton expansion, how it arises from eigenvalue instantons, we will be using this simple model called the Gross-Witten-Wadia integral, or the Gross-Witten-Wadia model. In particular, the instanton analysis in this model as explained by Marino and Dunn and Ahmed. Okay, so what's the setting? The setting is n equal to 4 super Young Mills on S3 times S1. And this theory has 32 supercharges. 16 of them are called Qs and 16 of them are called S's. And the Qs have the property that they square to the momentum. Roughly speaking, there are various indices that I have not written, and the S is squared to K. So S and K lower the energy of the state. So as you know, in conformal algebra, K lowers the energy of the dilatation operator. So S also lowers the energy. So you define a primary state, which is just the lowest energy state in a multiplet, to be annihilated by all the S's. And so it's also annihilated by the K. So one thing we will focus on are these so-called special states called half BPS states, where a half BPS primary is further annihilated by 8 of the Qs. So now it's annihilated by 16 S's and 8 Qs. So that's why it's the name half, because in principle, all the 16 Qs would have generated new states acting on this. So on these states, because they're very special, their energy, which is just the eigenvalue of the dilatation operator, equals the charge under a U1 subgroup of SO6, the R symmetry, global symmetry of this theory. So there's just one quantum number. Here I've called it K. And this Zn of Q is the generating function of just degeneracies of these states at a given charge K. So K is the energy, N is the SUN, or UN gauge group. Yeah, so that's the quantity. And first, I'm going to tell you the result at infinite N. So at infinite N, this thing takes the form of this expansion. It's like 1Q, 2Q squared, 3Q cubed, and so on. So they're just some integer coefficients, and they just tell you how many half BPS states you have at each given energy level. So what are these states? There's a Z, which is one of the scalars, one of the 6 scalars in SU in this Yang-Mills theory. You define A1, let's say, to be trace of Z, A2 to be trace of Z squared, and so on. So these operators have energy K. So energy of AK is K. And so if you want to write states with energy 4, you just make all these combinations, A4, A3, A1, A2 square, and so on. So there are 5 of these. So that's this 5 here. Okay, so that's just how you count. And then it's pretty easy to see that this is just the generating function of the partitions of integers. Okay, but the purpose of this talk is to study finite n, not just infinite n, but finite n. So let's say n is equal to 6. Yes.
You're looking at what? Q couples to what?
Q is the chemical potential that's dual to this SO6 global symmetry charge, which is also the energy.
H1 plus H2 plus H3.
I don't remember there's only this Z scalar lies in one plane of the SO6, right?
So you're looking at
just half BPS states, yeah. Okay. So this is the half BPS generating function. No, Z is an operator, so capital Z, sorry. Okay, this is, let me call it phi. So phi is one of the complex scalars of super Yang-Mills. So these are operators in the theory which are dual to states, and the states have some energy. Thanks. Okay, so But at finite n, like n equals 6, I'm going to tell you that this is what the answer looks like. The first coefficient is the same, q is the same, 2q squared is the same, 3q cubed, 5q4, up to this term, it's all the same. At this point, when you go to charge 7, this 15 in the infinite n theory becomes a 14 in the finite n theory. So this is saying that at finite n, there are fewer states. If you fix the charge and reduce n, you get fewer states. And the physics of this was actually referred to by Gautam in his talk yesterday. So at energy 7, which is where the first mismatch is happening, one of the letters which will appear here is A7, which is trace of phi to the 7. But since phi is a 6 by 6 matrix, because we are in a SU6, this trace of phi to the 7 only depends on 6 eigenvalues. So it's just a polynomial expression in the lower A's. So you don't get a new state, there is this reduction by 1. It's somewhat surprising that you don't get any changes here. So up to some number, the counting is exactly the same as the infinite n theory, and then the numbers start to reduce. So there's 22 here, and a 20 here, and a 30 here, and a 26 here, and so on and so forth. So the purpose of this giant graviton expansion was to recover the finite n result as a series of successive approximations or successive corrections to the infinite n result. Yeah. Yes, just as an example.
It changes at n equals 7 just because the first trace identity
is n equal to 7, yeah. And as you go to higher and higher things, you see there are also multi-particle states. So A7 you can never use. Therefore, when you go to higher charges, the numbers reduce by more. Like here there's a deficit of 2, here there's a deficit of 4, and so on. Okay, so the purpose of this giant graviton expansion is to start with the infinite n result and supply a series of corrections to get the finite n result. Okay, so that's the goal of the talk. Well, that's not the goal of the talk, that was the purpose of the giant graviton expansion. So let's see here, what does this giant graviton expansion look like? So they write Zn of q as the infinite n answer, brackets 1 plus this infinite series of corrections. And the first of these has the property for the half BPS case that the first correction is precisely this. So this GNM is this q to the n plus 1. Okay. And in general, this mth correction has this order. It's q to the mn plus m choose 2. So this was in the paper by Samir Murthy. Okay, so in particular, this first correction is like q to the n plus 1, so it looks like e to the negative n log of 1 over q, if you think of q to be much less than 1. So this thing looks like an instanton effect of order e to the minus n, as opposed to certain other instanton effects which could have been e to the negative n square. Okay, so this is the first observation. So now another fact is that since this quantity Zn of q is an index, it's independent of lambda, the 't Hooft coupling. So we can compute it in the free theory or in the infinite n theory, or infinite lambda theory. At lambda equal to 0, this path integral can just be done, and the whole expression reduces to a single integral over an n by n unitary matrix U with a certain integrand. The integrand here depends on q, and there are infinitely many terms of this nature, trace u to the k times trace u to the negative k. And the point of this talk is going to say that these e to the minus n effects are eigenvalue instantons in this matrix problem. Okay, and I would just like to make a comment at infinite lambda. At infinite lambda, this theory is dual to ADS. And what happens in ADS is that these e to the minus n effects are D3 branes that are wrapping some S5. And it was shown that there is a maximum R charge that one of these D branes can have, which is n. So this minus q to the n plus 1 represents the absence of a giant graviton with R charge n plus 1. So in the infinite n theory, you've overcounted the giant gravitons, and this minus q to the n plus 1 is like the first saying that you should not really have had that giant. But we will not work in gravity, we are only going to do just these kind of integrals. Okay, are there any questions about the goal of the talk? Yeah.
Introduce the Z as being defined by the dimensions of the subspaces of BPS states with a certain energy.
Yes.
Coefficients. The then you have this expression for Zn of q that you said you got from a path integral.
Yeah. Well, it's the standard thing how the path integral reduces to Hamiltonian expressions for partition functions. So the theory is on S3 times S1. So this is just counting specific states in S3 times S1. So right, when you calculate Z of beta using a path integral,
then there's some like insertion in the path integral to project onto the BPS state?
Yeah, all that, yeah. Yes. Yeah, all those things you can write down. There are a lot of, for this particular half BPS case, I could have even written down a formula for Zn of q. But the thing is so simple, but I didn't want to present it because it kind of misleads the point of the talk. Yeah, for finite n you can write. For this special case, it's kind of easy to write.
N particles in a harmonic object.
And
Free energy of n particles.
Yeah. Yes. Well, we will see that this expansion is actually convergent. So in some sense, you're summing over infinite number of these m's, and this is a convergent expansion. This is not some asymptotic expansion. So you could write some other expansion. Of course, a given function can have many, many expansions, and in some other way of writing it, there might be those effects. You can already see that when m gets of order n, you kind of, but the point is you should really think of these as supplying corrections to the infinite n theory. And n is just some formal power counting sort of thing. Okay, so let's go on and then start to get into the details. So what I have done here is defined a general integral. So here the couplings were all controlled by a single number. We can study a slightly more general integral, which is this Zn of g vector. G vector is a collection of infinite number of couplings that I'm calling gk from 1 to infinity with the same kind of potential. And the first thing we use, in the end, we don't have to use it, but this is the simplest way to present the results, is you do kind of a Hubbard-Stratanovich decoupling of this product. So you write this as an integral over two complex variables for each k with this Gaussian term and something which is now linear in lambda k and linear in trace u to the k. So if you did the lambda k integrals in this line, you will get back that result. The point of this is that now this is a single trace potential. It's some trace u plus trace u inverse rather than a product. Okay, so the prototypical example of this is the Gross-Witten-Wadia integral. Penta is here, which is defined as follows. So this thing first arose in studies of 2D QCD. It's a function of two numbers, n and what we can call the 't Hooft coupling t. It's some matrix integral over n by n matrices with this n over 2t times trace u plus trace u inverse. So basically what we're going to do now, I'm going to explain the instanton effects in this model and then push them through this Hubbard-Stratanovich trick, and that'll be the answer. So that's like the goal. But we'll see that we'll have to be a bit careful, and the derivation I will present will not be rigorous. There will be some approximations, and somehow you land on your feet. So I think more work needs to be done to make this approach rigorous, but I'll just present what we have. Okay, so the first thing you do in any kind of matrix integral like this is you write it in terms of eigenvalues. So thetas are angles from 0 to 2 pi. You get the eigenvalues, you get this van der Mond. And then this thing just becomes a cosine of theta I. Okay, and then, which is very important for us, was important in this paper with Chitrang and Dan, is to actually write this as a holomorphic integral. So this absolute value squared does not make it look holomorphic, but this is a number times its conjugate, and they have absolute value 1. So I can replace zj star by 1 over zj. So when you do that, you get a integral over dz. So all the z's are integrated over the unit circle in the complex z plane with this standard looking van der Mond and this potential. The price you pay is that there is this zi to the n here. That just comes out, we could do it, but just believe me. So there is this non-standard factor here, but the van der Mond becomes standard. Now the point is this is a holomorphic integral, so I can start deforming contours and things like that. And I've just defined a potential here, minus 1/2 z plus 1 over z. It's like negative cosine theta. It's just the thing that sits here. Okay. So, yeah. So there's a question here. Yeah, sorry. All the zi's are integrated. So, yeah, there are n integrals. Yeah. So basically the point is that you can generalize the computation I will present to include an arbitrary number of couplings and then push it through this Hubbard-Statanovich to get your answer. Okay, so the next point is, sorry, question? Yeah. So, sorry, say that. Yeah. Yeah, there's some logarithmic correction to the effective potential. No, so we'll see that because this is literally equal to this, right? So it yeah, we'll see that. You're right that the z equal to 0 will become a special point, but it will not cause really any problems in the. Sorry? No, it's just on the unit circle to begin with. Yeah. Okay, so the point that was first appreciated in the original papers already is that this model has two phases. So if t is small, the potential has a 1 over t. If you look there, the potential has a 1 over t in it times cosine theta, right? That is what the exponential has. So it something looks like exponential of n over t cosine theta. So this is maximized near theta equal to 0. So what the eigenvalues want to do is basically all end up at theta equal to 0. So all the eigenvalues want to be at that point. But because of the Vandermonde, they spread out a little bit. Okay, so these are the eigenvalues. There's some endpoint which you can determine as a function of t. And in this phase, there's an instanton that sits here. That is basically, I'll explain that later, but if you pull out a single eigenvalue, it feels not only this bare potential, but because of that Vandermonde, there's like a collective force on it. And that collective thing has an extremum here. Okay, so this is the small t phase. We will not be interested in this phase. So that's when the potential is very steep. The potential is very steep here, so all the eigenvalues go here. Now when t is big, in particular t is bigger than 1, what happens is that the potential is getting weaker, which means that the Vandermonde repulsion is getting stronger. So this cut starts getting bigger and eventually sort of covers the whole circle. Okay. So the eigenvalue distribution is not uniform but has some profile. So now you can ask, what happened to this guy, the instanton? What happens is you get two instanton locations that are off the original contour of integration. So this is the original contour of integration where the eigenvalues are spread out. But if you analyze the effective potential, you kind of get complexified instanton locations off in this side. Okay, so we will be interested in this phase and describe the eigenvalue instantons in this phase. Okay, so the first point which has to be really appreciated is that once you have an eigenvalue distribution that splits the complex plane into two disconnected regions, the resolvent has two different definitions. So the resolvent of this matrix, I can define one resolvent, which is 1 over n trace of 1 over z minus u for mod z bigger than 1, and an r minus of z, which is 1 over n trace of 1 over z minus u for mod z less than 1. And this thing you can compute by expanding in powers of 1 over z. Because z is big, u kind of has, you think of it as order 1 because it's on the circle. So it looks like 1 over z plus 1 over z square times 1 over 2t. I'm just giving you an example. You just basically expand this in powers of inverse z and calculate the moments. It's easy to do in this phase. Yeah. We'll come to it. Yeah, it's one of the eigenvalues that has been pulled out of this n eigenvalues. Yeah. Yeah.
The double trace model that you started with,
Yeah.
the second saddle point is just uniform.
Yes, it's uniform.
So you'll presumably see this when you do your.
Yeah. So exactly, right.
So we just want to solve this for the uniform.
Well, that is you could do if you didn't do the Hubbard-Statanovich, right? Because there, you see the integral over lambda is at the end. Right. So I can solve the problem for each lambda and then do the integral.
But presumably the saddle point on lambda is going to be 0 or whatever gives you uniform.
Yeah. So
you only really need to solve it on that.
But the point is going to be that in the end of the day, the final answer is not going to come from a saddle point. You're going to have to do a full contour integral to get the answer. So there's no saddle point approximation for that double trace integral.
So without doing this Hubbard-Strauss dynamics, I could have started with this double trace and then try to work around.
You can, and it's there in the paper, but I'll not have time to explain it today. There's something you can do and follow. You can get it directly with the double trace.
And then is it like one eigenvalue away from Yukawa?
Yes, but that one eigenvalue does not find a stationary point. It's integrated still over a unit circle which is slightly less than 1 radius. And actually, it's a 2 instanton effect. We'll see. But here the point is that here you have to do a different expansion because U is the bigger guy and Z is smaller. So this thing, you have to expand in powers of inverse U and Z is in the numerator. And you just get minus 1 over 2t. So you see these two resolvents are different. And the discontinuity across the unit circle will give you the density of states. So rho of theta will be r plus of Z minus r minus of Z over 2 pi I dz by d theta. And for people who are familiar with this is 1 over 2 pi, 1 plus 1 over t cosine theta. Remember that t is bigger than 1, so this is always positive. Okay, so it's very important to keep in mind that after you've defined this function, outside the unit disk, you can analytically extend it anywhere, right? It's just an analytic function of all z. Similarly, this is a bit like retarded and advanced Green's functions in a theory where the spectral density has support on the whole real axis. They're just two different functions. They have nothing to do with each other, and that's it. Okay, so now we come to the effective potential. So what is the effective potential? As I already said, there's a cosine theta term in the bare potential, and there is this van der Monde repulsion, and there is that z to the n downstairs. So if you put all of that together, I'm just going to give you the result because I can't present all the details. V effective plus of z comes out to be minus z over 2 plus 1 over 2z minus t log of minus z, and actually V effective minus comes out to be just the minus of that function. So z over 2 minus 1 over 2z plus t log of minus z. It's hard to see what these look like, so let me draw them for you. So this is a unit circle just as a guide to the eye. There is this thing, there is 0. So the V effective plus looks like this. So this is a plot of V effective plus on the negative real axis. Okay? And V effective minus, since it's just the negative of it, it's looks like that. Okay? And lo and behold, we have found 2 candidate extrema in V effective plus and 2 candidate extrema in V effective minus. It's the combination of the cosine theta and all those zi minus zj squares downstairs. So you exponentiate it, you get some log, the standard Coulomb repulsion. Okay, so now you could ask, candidate instanton location is this one, right? But putting it an eigenvalue here would be really bad because it has negative effective potential. So when you put it there, you get an enhanced contribution to the answer. And actually you can see that the steepest descent contour goes straight, so there's no way to actually deform the contour to this steepest descent contour of the saddle point. But this is okay. So you actually get a saddle point, an eigenvalue sitting here. Now notice that there is something slightly strange about this, because V effective plus starts out its life being defined for z bigger than 1. But somehow the relevant saddle point is in the other region. That's okay, right? And this is what Marino and Schiappa and Schwick in the recent literature have called ghost instantons. So it's like you started with some analytic function and then extended it, but then you found an eigenvalue instanton in that region. Similarly here, putting an eigenvalue instanton here would be really bad because its action is negative. So you actually put one here. Now, it is a fact that that was appreciated before, but we explained it in maybe some better terms, why the one instanton effect in this phase is actually 0. So the leading instanton effect comes from 2 eigenvalue instanton, one placed here and one placed at this location but feeling the V effective minus. So let me give you the result of the calculation. So Z, yeah. Because you can show that the contribution of one instanton is just 0. There's a prefactor that you get, which is just 0. And another way to explain it is that these plus and minus, really, there is a dual string theory to this in the double scaling limit. And that string theory has D branes, which have R charges. There's a Z2 R charge. So you need to have total 0 R charge for anything. That's like a one way to say it. Anything with just positive R charge will just be 0. Okay, Zn of t is some 0th order contribution. 0th order, I mean no instantons. And then this instanton with one positive instanton and one negative instanton. And that looks like follows. So this thing you can compute is just this, the first term, plus this guy, exponential. So it starts like this. Times a minus sign, e to the minus 2n s of t times 1 over n times t over 8 pi t square minus 1 to the 3/2. Okay, so this is the perturbative, the 0 instanton contribution, and this is the 2 instanton contribution, where s of t is the function arc cosh t minus square root of 1 minus 1 over t square, and whether t was bigger than 1. Okay. So what we learned is that this is like a 1 comma 1 instanton contribution. And I want to write now where this came from. So this answer actually came from doing the following integral. dz1 over 2 pi I minus dz2 over 2 pi I exponential of minus n over t v effective plus of z1 plus v effective minus of z2 times 1 over z1 minus z2 square. Well, roughly you can think because there are two unstable instantons. So each unstable gives an I, so there's a minus. Yes, the minus is a one loop thing. And you need the minus sign to get that minus q to the n plus 1 eventually. Okay, so I should say a few words about how do you get this expression. So there were n integrals over z's. The point is you do the n minus 2 integrals. When you do the n minus 2 integrals, there are terms that couple this z1 and z2 to the n minus 2 eigenvalues. That is some moment that you have to calculate in the subproblem where the size of the matrix was n minus 2. So that will give you some moments of things that depend on z1 and z2, and that produces for you this extra factor downstairs.
Z1 and Z2, the locations of the two instances?
Yeah, so the z1, I should maybe draw here. Yeah, z1 is being integrated on the blue line here. So this is the contour for z1, and there's a contour for z2, which is like that. If we so chose, we could now deform it to the saddle point, if there was a saddle point. But these are the contours. So this is still an integral. I have not done any saddle point. Going this arrow is taking the saddle point approximation.
So force between Z1 and Z2
Yeah. I mean, that's just two particles, right?
they're behaving almost independent and leading on.
Right. But there is this coupling between them. Yeah.
Which is one loop.
Yeah, one loop. But one loop effects are going to be important for us. So we're only going to calculate everything to the saddle point action and the one loop term. Okay, now the only point of going from here to the final answer is just that, first of all, I only presented this for this Gross-Witten-Wadia model, which has a single term in the potential. You can first do the same process for arbitrary lambda k. You get some effective potentials, which are functions of lambda k. And then you note that this n over t, was like the lambda k there. So the n over t is the coefficient of the single traces. So a very important point is that even after you write that Z1, Z2 integral, in the exponent, the thing is still linear in lambda k. Okay? So after you do that, you will have all these integrals over lambda k and two integrals, one over Z1, one over Z2. Now just do the lambda k integral first, because it's still Gaussian, right? This is quadratic, that's something linear. You just do the Gaussian lambda k integral. And the output of that is the following. So this gn1 of q for the, I'm just, yeah, for the half, let me just write the result for the half BPS case. You can find the more general expressions in the paper. So there's a minus sign du over 2 pi I u to the negative n dv over 2 pi I v to the n 1 over u minus b square exponential of minus sum over k going from 1 to infinity q to the k over k 1 minus q to the k 2 minus v over u minus u over v. This step is not supposed to be obvious when you have to do some work, because I haven't given you the expressions for v effective, for general lambda k and so on. But you can do this and this is what you get, okay? So I just replace Z1 and Z2 by u and v. So this is the actual answer for Samir Murthy's first giant graviton expansion. This can be generalized to m things. So let me actually write, because it's interesting to look at. So to get this g and m, yes.
So now you've done the integral over your Hubbard's Tadashi.
Yes, lambda k's, yeah.
So now this should be sort of what you would have got just in the double trace by itself.
Yes, yes, you can do that. And you can show that if you just pulled out these two eigenvalues from the double trace potential, you will still get this. Don't try to do the saddle point too fast. That's the only point of this paper. Like, pull out the eigenvalues, let them roam around their contour. Like, that's it.
Right. So in your single trace model, there was an effective force felt because of the background eigenvalue.
Yes, yes, yes.
That was a large effect.
Yeah.
Can I think of it as in the double, when you put in the double traces, it's only like a two-body interaction?
Yes, 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 that is true, yeah.
Okay.
Yeah.
Yeah. And that's why there's a one.
Sorry?
That's why I don't see an n.
Yeah, there's no n, yeah.
N, because it's just small two-body.
Yes, yeah.
Okay.
Yeah. Yes. Well, that's by definition, right? Like the leading large n is no instanton. The instantons are suppressed. Okay, so this thing gives you minus 1 to the m over m factorial squared product over I from 1 to m dui dvi over 2 pi I ui to the negative n 2 pi I vi to the n ui minus uj square vi minus vj square divided by ui minus vj squared exponential of minus sum over k from 1 to infinity 1 over k gk over 1 minus gk sum I from 1 to m ui to the k minus vi to the k times sum I from 1 to m ui to the negative k minus vi to the negative k. Okay. So
Sorry, what was it?
well, I wrote it here. It was this mth correction to the. It's like you can think of it as 4 instantons, 6 instantons, 8 instantons. So the G and M comes from a 2m eigenvalue instanton. M are inside, M are outside. You have M positive charges, M negative charges. So that is why this Vandermonde has this structure. Like charges repel each other, they are in the numerator, and the unlike charges attract each other. So they come in the Vandermonde with the opposite sign. So this thing looks like an integral over an m/m supermatrix. Okay, 5 minutes left. What I want to show you, I hope you can see that this just becomes this when m equals 1, right? That's clear. There's just one term here. You multiply it out and you get that. I want to show you, just erase this part. And how do we get that q to the n plus 1, to complete the loop on the story? So the q to the n plus 1 will come from doing, okay, so I should draw the u contour and the v contour. The u contour is here, the v contour is here, u and v, 1 is here. Okay, so you take this result, you take gn1 of q, and you do the u integral by poles. By poles, deforming the u contour inwards. Okay, so you can take, for example, q to be much, much less than 1, and the first thing you have to do is you have to first rewrite this a little bit. This is still not in the form of poles. It's actually an easy exercise to put this thing in the numerator, rearrange this sum and so on, and write it in this form. du over 2 pi I, dv over 2 pi I, u over v raised to n, 1 over u minus v square, product over n equals 1 to infinity, 1 minus q to the n whole square over 1 minus u q to the n over v, 1 minus v q to the n over u. Okay, so we pick out the pole at u equals vq. Okay, that has absolute value less than 1. That's from this term here, the n equals 1 term here. So you do the pole, you are left with a v integral. It's just 1 over v. Take the, yeah. Q to the n plus 1 over 1 minus q. So this is just 1 now. So this is minus q to the n plus 1 plus order q to the n plus 2. Okay. And I should say that this super matrix form of this giant graviton correction was not written in Sameer's original paper, but was in a follow-up paper, a single author paper by Dan Enicheku, who's the student at Stanford, and a paper by Liu and Rajappa. So it takes some work to convert Sameer's expression into this form, and this is the form that pops out. So this work of Dan and Liu and Rajappa was actually crucial to connect this to Sameer's result. But you see that at the end of the day, you just have an integral like this. It's just some poles. It might be hard to do it, but you can recover these results. Okay, so that's how you get these finite n corrections from these eigenvalue instantons. Okay. I wanted to make a couple of comments. Sorry, I want some water first. One thing is that note that I said that this derivation is not rigorous, right? It's not rigorous because here we just truncated this, this expansion, these terms, which came from doing the integral over the n minus 2 variables to one loop. We didn't keep the 1 over n corrections. Somehow you don't keep them, but still you get the exact convergent result. So you make like 2 mistakes and somehow you get the right answer. Any other comments? I guess no, just one mistake. You just keep only the one, you push through the integral, so maybe you swap some things, yeah, yeah. Okay, thanks.
Sorry, so
yeah.
The answer to this should be something, an integer.
The answer to this, well, yeah, the power series expansion of it is always integers. So if you expand it in further powers of q, this is not just this, right? So it has more terms that I have not written down, and they're all integers. So you can check.
Term by term.
Yeah, it's integers. Yeah, but it's important that if you just took the first correction, it will not be the whole story. You'll have to take the second, third, fourth, all of them, resum them, get the full.
That would not be obvious.
Yeah, it's not obvious. Yeah, right. Yeah. Okay. Thanks. Yeah.
Hello. Yeah. So these minus signs that you get with every 1,1 instanton. Is it saying that the 1,1 instanton is in some sense some effective fermion or something, or what is the?
Well, I wouldn't say it that way. Maybe it is, but my interpretation is just that if you're sitting on this saddle point, right, the steepest descent contour goes vertical.
Yeah.
So that's an I.
Yeah, I understand the instanton, but if you want to think about it in, let's say, just in terms of the eigenvalues on the circle, without analytic continuation and so on, I'm wondering what does it mean? You also get a -1 to the power m for the m comma m instanton.
Yeah. You're right.
Okay.
Yeah, good point. I have no useful comment about that. Yeah.
There's another representation to the same answer.
Yeah.
Which is that it's basically just put n particles in a harmonic oscillator potential.
Right.
You just compute the partition function of n bosons, identical bosons in a harmonic oscillator potential. And then you could write down the partition function for arbitrary number of bosons with a chemical potential for particle number and project down to n by doing an integral. I was wondering whether you could analyze that integral in some sort of, I don't know, similar way and see that you get the same thing.
Yeah, I should say I'm not intimately familiar with that description of the system, but maybe we can chat about it. Let me not make any comment. No, there is also some description in terms of fermions, right? Like in a n fermions filling up a Fermi C, and the giant graviton is some hole in the Fermi C and things like that. So I'm not sure how to connect these to those words. Yeah, Gautam has a question.
Well, yeah, so when you have these multiple Hubbard-Stratanovich parameters, so you have this, polynomial action there in terms of single trace guys. So, there's a rather complicated multi-cut solution structure in those cases. So, for example, the resolvents are more complicated with, multiple branch cuts, and they don't affect your analysis.
Yeah, at least doesn't seem like they affect the analysis. Because we are in this phase where these couplings are very big, essentially. So then roughly the phase that dominates is the one where the eigenvalues are just over the whole circle. So somehow the only phase...
Is the first one that you encounter, is that?
Yeah.
I see.
Okay, if there are no further questions, let's thank Raghu again.